Welcome you to today's lecture. Today we will start looking at conversion of transfer function to state space. So converting a transfer function to state space. Now so there are two actually types. One is transfer function where we represent our system, and other is known as state space. Now a transfer function actually use the frequency domain representation. State space is a time domain representation. Secondly, a transfer function is a unique representation for a particular output to input ratio. What this means? This means that if I going to write a transfer function for a particular output to input, I get the same result if someone else do it for same input. So it normally have unique, but state space you do have multiple representations. I give you a simple example. You can do transformation due to transformations. For example, you can use model decomposition. Okay. You can use eigenvalues decomposition, someone says, and etc. So because of the decomposition, you can change the matrices. So that's why they have more than one representation for a single system. So this is purely for LTI system. So they can have for nonlinear, LTI, time varying, so this means that state space representation is much stronger for representing all type of dynamic systems. So this is known as classical control, and this is known as modern control. So state space normally using modern control representation. Now today we will look at how we can convert a transfer function to a state space representation. Now for starting this, so if you remember, if we have a dynamic equation, okay, so if we have a dynamics and if I to have the nth order derivative plus so on plus a1 dy by dt plus a naught y is equal to b naught u. So this is the equation. Now how we do it for this differential equation, how we convert into state space. What we do, we look at the highest derivative here. It is n, so we need n state variable, but we start assigning state variables not from the highest derivative, below the highest derivative. So we start x1 equal to y, x2 equal to derivative of y, and so on up to xn, that is actually equal to n minus 1 derivative of y. So this is the way we can assign it, and after that we just do the derivative of these state variables that give us x2. Similarly for x2 dot is second derivative, that is equal to x3, and so on up to xn dot, that is give us the nth derivative. So that's why we have to write derivative till state variable till n minus 1 derivative, not the nth. So this is the way we can represent in terms of state space. So from here, so we just take this, write this on the other side and take this all terms on the other. It becomes minus a n minus 1 x n, okay, then minus a n minus 2 x n minus 1 minus so on up to minus a naught x1 and plus the input term, that is b naught u. So this is the way we can represent any differential equation in terms of state space form. So this is our state space form, that is x1, x2, take the dot here up to xn dot. This is equal to dynamic, it becomes 0 1 0 and so on up to 0, again 0 0 1 0, so on up to 0. So it's come here 1 and 0 here, 0 here. Okay. So this is the way we can represent. Last line is actually this equation, that is minus a naught minus a1 up to a n minus 2 and a n minus 1. So this is the way we can write the A matrix. Then we have to put x1, x2 up to so on up to xn. So plus then we have to write the input matrix. So input is, there's nothing with the input here, 0 0 up to last one is the b naught and input is u. Similarly for output, if we want to look at some output, so if we want to look at the first x1 as the output, so this is 0 till 0 and we have to multiply x1 up to xn. So this is a state space representation to overview you what it is. Now what we are interested is to how we convert transfer function to state space. So I write in symbols TF for transfer function and SS for state space. Now how we do it? Let's consider a very simple example here. We have a transfer function that is written in this form. Nine s square plus 26x plus 24. Now the how we do that? Just do cross multiplication. So cross on both sides. So when we do that, we have to multiply c of s by s cube plus 9s square plus 26s plus 24 equal to 24 times r of s. After that apply inverse Laplace transform. Okay, so when we do that, it be because S3 represents the third with, as we know that this is transforming initial conditions are 0, so when we do that, it says this is third order of C2 plus 9, second derivative of C plus 26, first derivative of Ct plus 24 C of t equal to 24 R of t. So this is the relation we get. Now, okay, we can rewrite it as C triple dot equal to minus 9 C double dot of t minus 26 C dot of t and minus 24 C of t plus 24 R of t. So this is what we get. Now we can make block diagram of this as well, because this is the third derivative, so there are few terms adding in it, so we make a block here, and this is the first term that is adding is the input, that is multiplied by 24. So this is the first input with the input RT is multiplied for 24 and add in it. After that, we say that assume that this is the result we are getting for third. Now if I do integration here, I do integral, okay, what I get C double dot. If I do another integral, what I get C single dot of t. If I do another integral, what I get C of t. Okay, so now we say that output is our C of t, so this becomes Y of t as well. Now after that, because C of t multiplied 24 with minus make this term, so we start with the highest one, second one is with 9, we put here and put minus sign because of this. Then there is a 26 with double dot, put 26 and add here with minus sign, and the last one is with 24 here. So this is the block diagram that you can make using the differential equation. Now next step is, I told you how to write the state space from the differential equation, so this will help us to write the transfer function into state. So I just rewrite the equation so that we can use it. Double dot, again minus 26 C single dot of t, again minus 24 C and plus 24 R. So this is the relation, so it is a function of time, so it's better to write t. Now I told you to assume state variables. So we have to assume how many state variables? 3 state variables, because of the highest derivative tell us the number of state variables. Now we need 3 state variables. Now for that we assume let x1 equal to C of t, x2 equal to C dot of t, x3 is equal to C double dot of t. So this is the first thing, and then take the derivative of x1 off. So x1 dot equal to C dot, that is equal to x2. Similarly, x2 dot equal to C double dot of t, that becomes x2 dot that is equal to x3, sorry, not dot, this is x3. Okay, this is your x3 of t. Now last one is x3 dot, that is equal to C triple. Now I have to use this equation, so from here this becomes minus 9 x3 of t, because x2 dot is x3. Similar 26 x3 dot is x2, so it becomes minus 26 x2 of t, then minus 24 x1 of t, then plus 24 r of t. So this is the way you can write. Now represent in matrix form x1 dot x2 dot x3 dot, okay, bracket here, put equal sign, then make a matrix. Then you have, if this is a derivative, you have to write the state variable here, the 3 state variable plus, then you have a single input, put input here. Now from here x dot equal to x2, so it becomes 0 1 0. Similarly x2 dot equal to x3, so it becomes 0 0 1. Last one is x3 dot, we have to write from here, so we have to start from here. It is minus 24 minus 26 minus 9, so also have the input, that is 24, other do not have input, so 0. So we also define the output, which is in block diagram is the x1, so it becomes 1 0 0. You have to multiply the derivative with x1 x2 x3 state variable here. So this is the way you can represent from transfer function to state space form. Now next thing that we need to do is to convert from state space to state space to a transfer function. Now if I wrote the generalized formulation of state space form, this is the thing that we have. This is the state space form. Okay, now I told you how we do that. We normally take the Laplace, so apply Laplace transform, because transfer function is actually in frequency domain. For that case we have to apply the Laplace. When we apply the Laplace transform on x dot equal to ax plus bu, okay, what we get? We get similarly Laplace transform on y is equal to cx plus du. Now let's write here, because we are finding the transfer function, so we assume initial condition equal to 0. So in that case we have s times x of s is equal to a times x of s plus b u of s. Okay. From here, if we do a little manipulation, so we can write it, we take this and this side, so x of s, because these are matrices, so we have to multiply the identity matrix so that we can do the subtraction, is equal to b u of s. Or we can say that x of s can be written as si minus a whole inverse b times u of s. So be very careful about post and pre multiplication, because these are matrices. So you know that from algebra that AB is not equal to BA. So this is very, very important. So be very careful about the post and pre multiplication you are doing here, because here you have to multiply the pre so that you have all the states are same. Now if we apply the Laplace here, it becomes y of s equal to c x of s plus d u of s. So you know that the transfer function is a ratio of output to input. Output is y, input is u, so we have to put values of x of s here. So it becomes y of s. From here we can write the value, that is si minus a whole inverse b u of s plus du of s. Let me rewrite the plus here. Now it's better. Now if I take out the u of s and take the ratio y of s divided by u of s, so the transfer function becomes c times si minus a whole inverse b plus t. So this is the transfer function. In state space you already know the matrices A, B and C. So you just plug in to this relation, you calculate the transfer function. So this is the conversion that we can use from state space to transfer function. So I will stop here for this particular video. Thank you.